So next speaker is Steve Selkowitz. He's a retired senior advisor for building science and the former leader of the Windows and envelope materials group in the Building Technology and Urban System Division. As an internationally recognized expert in window technologies, facade system and daylighting, he collaborates with R&D teams worldwide. He's a frequently invited speaker here at GPD and everywhere. And a professional, he works also with professional groups, many aspects of building technologies and commercial building energy efficiency. And is the author of over 170 publications, 3 books, and holds 2 patents. So the presentation of Steve is about unplanned obsolescence and the looming threat posed by facade to future building performance. Steve, very happy to have you here.
Thank you. So that was a threatening title. Thanks for the intro. We kicked around the title a bit. I think we aren't threatening the future here. We're kind of looking at what's going on in the future, what's coming. My colleague here, Mick Patterson, some of you I hope know him. He's been in the facade business for a very long time. In fact, I figured, we're talking about some 100-year building issues here. Between Mick and I think we have about 80 or 90 years of experience in the building industry. So I will jump right in here. What we want to do is take a look ahead at where we are and where we're going and what's coming, and look at the envelope, the facade of the building, and look at buildings generally through the sort of lens of climate change and energy and all the other policy issues driving us now. And to be blunt, we don't have the answer, but we're trying to raise questions and start a dialogue, and maybe in 2 years at the next GPD we'll have more answers. So let me charge through some of this, and this time at the end we can talk about some of it. There's clearly a global challenge in terms of climate change. You've heard that in multiple presentations in the last day or two. Buildings are about half of the problem. There's an overlapping but distinct difference between operating energy and carbon issues and embodied energy and carbon issues. If you look at the operational issues, this is sort of energy use. And so I'm going to bounce back and forth between US numbers and global numbers and European numbers. Most of what I'm going to give you is sort of the US, but it's frankly similar in Europe in most cases. So on a national basis, the energy used in buildings is about 40% of US energy use. If you look, though, at urban centers, New York City, the number is much, much higher because mostly are about buildings there. The right-hand images there give you a flavor of, the top one is some fires in California a year or 2 ago. The bottom one on the right is, in fact, we saw one, I think, with Europe, what Europe might look like in 2100 with a lot of lowland flooded. Well, this is the equivalent in the US. I have to make a parenthetical political comment here. If you follow politics in the US, you've got Texas and Florida that, to first order, don't quite believe in climate change yet. And those are the folks that are going to be underwater in 2100 if we don't do something. So if we take a look at the full economy and look at buildings, as I said before, buildings are about 40%. One of the problems is when people generate charts of where energy goes in buildings, and you end up with a chart on the right that you've got heating, cooling, lighting, and so on. You don't see facades or envelope typically because they aren't plugged into a wall and don't consume electricity directly or gas. But if you look at the ones in the red boxes here, heating, cooling, and then lighting, ventilation, they indirectly impact these. So they're critically important, but they're often not counted in the way that might draw some kind of attention to them. In the US, this turns out to be about $50 billion a year in terms of cost of energy use. If you take the commercial sector, for example, and you do a what-if analysis on the entire system, you say, so here's the existing stock here costing about $20 billion a year, and you go through a series of what if you do better products, if you do all low E, if you magically replace every window with low E, if you go to a dynamic glazing, and so on and so forth, you go down the list, you see that the energy costs get lower and lower, and actually you get to the point where you have a net positive, and that's because your windows have very low heat loss, they're using solar gain in winter, passive heating, and you're using daylight and maybe some PV on the facade. So we have the potential of going from a sort of a $20 billion a year cost to a $15 billion a year savings. Now, a lot of emphasis has been on the new net zero carbon or net positive carbon. So I just grabbed a graphic from a study done in the US recently. These are just the attributes of a carbon neutral building. And I think on one of the earlier presentations, there are requirements in Europe for many buildings or all buildings to be net positive or net carbon positive by 20XX, by 2030. And we have these things in the US as well. And the list on the left there is kind of, what does that mean? Well, energy efficiency is the first one there. That's critically important. No fossil fuels, decarbonizing. I'm going to come back to that in a minute. And then the one on the bottom is getting increasing attention in the facade and glazing world, but in the buildings world generally, looking at the embodied carbon. And here you see all the pieces and parts of the building that we're kind of talking about. Now, this is generally this net zero neutral carbon is for new construction. But in the real world, in terms of what's happening, we have to pay attention to existing buildings. This is a recent study in the US. It's just looking at what's happening over time. This is over the next 30 years. The existing stock is in blue. It decays slowly over time. Of course, some of it's renovated or retrofit. And then you get the new construction there, which is that green piece of the model here. Do I have a... No, I don't. Sorry. Backwards. So the current, in the US, the numbers are new construction is about 1% to 2%, and renovation retrofit varies a bit, depends on location, city, and so on and so forth. But in general, for a long time, we're going to be stuck with the existing building stock we have. So we need to do something about that, and I will come back to that later. And the reason I bring this up also is because in terms of decisions about embodied energy, you have a little more control in new construction than in existing construction. But we'll talk about that too. Now, there have been a lot of interesting papers in the last day or two here on the embodied versus operating energy. This is clearly, carbon rather, this is clearly an important aspect. There are a variety of LCA life cycle assessment models and tools that look from cradle to grave. I'm sure many of you are familiar with these. I just want to point out that there's a lot of subtleties and complexities here, and they change over time. And this is not an area that I'm expert in, but I think it's just important to be careful when you see a study that claims such and such an effect or whatever, be careful about the parameters, be careful about the implicit data behind it. So as an example here, the carbon intensity of energy sources. Snapshot today in the US again, quite a bit of our electricity comes from burning coal, but that's rapidly declining. PV and wind are coming up. So the carbon intensity of electricity is not only changing over time, it changes regionally and locally. And equally important, on the second bullet here, it changes with time of day. In California today, if you're using electricity at 2 in the afternoon, a good chunk of it is PV, is solar. And so the carbon intensity of a kilowatt hour used at 2 in the afternoon is quite low. It could be almost zero. But if you use the same kilowatt hour at 9 in the evening and the wind doesn't happen to be blowing, it could be a gas-fired plant or something like that. So if you do the analysis properly, and there are studies that do that, they'll look at the time dependence of the end use. And this gets into a lot of other issues about how we manage the time-dependent use of energy in buildings generally. If you look at the manufactured product side and look at the embodied energy, you have embodied carbon, you have sort of similar issues. There's a wide diversity. If you look at a frame of a window, you can choose between wood, PVC, aluminum, for example, and then if you look at some of them like aluminum, well, was that aluminum from ore or was that recycled? And the differences, if you look at the embodied energy numbers between these, are not 5% or so. They're like 200%, 300%. They're very large. So it's just a caution when one looks at these numbers to be sure that we're looking or we're talking about the same kinds of things. And then just this issue of operational versus embodied. I mean, we hear people already saying, well, you don't want to go from double to triple because the embodied energy going to triple is more than the operational energy savings. It might be, but it might not be. It depends on these parameters like climate, window to wall ratio, and so on and so forth. There's been a very nice study done in the last few months between Saint-Gobain and Arup. And I just pulled one that's an 80-page report. They looked at 14 different curtain wall systems. They looked at a lot of the variables I just talked about. And I just wanted to show the spread here. This is operational energy on the horizontal axis, embodied energy in the vertical axis, and huge variation, sort of 3-to-1 on the vertical axis and 5-to-1 on the horizontal axis. And so the point is, if you see a quote somewhere that embodied is twice as important as operating, well, it might be, but it might be half that or it might be twice that. So just be careful about what the assumptions are. One of the nice things about the report is it documents those details and assumptions very, very nicely. The interface between embodied and operational gets us into the life cycle of the building. And this is another whole interesting, complex area. Here's sort of my take on that a little bit. I mean, on the right-hand side in blue here, there's the starting with the requirement for the building when an owner comes to an architect and says, I'd like you to do this new building, to the point where it's built and ready to be occupied. This is a time frame of, I don't know, 1 to 10 years. If it's a simple building, it goes quickly. Large projects can take up to 10 years to get underway. I mean, some probably more than that. And then you've got the operational side, which, from the point that they're occupied to, 50, 100 years out, and a lot of these things going on here in red. The renovation rehab piece up here isn't well developed, but there's obviously a lot going, or there could be a lot going on there, aside from just normal maintenance. There could be a lot going on there. This was part of some projects we were doing looking at data needs, that your ability to intervene, to operate the building effectively over many, many years, and to intervene at points and change things, partly depends on your understanding of what the building is. I mean, the people who operate the building in year 23 were probably not the people that worked with the design team 23 years before that. Do they have the data and the understanding of how the chillers work, of how the vending windows are supposed to work? So there's a information requirement here, data requirement here, that will, I think, only get more complex over time if we start to pay more attention to the operational aspects of the buildings. So if you step back then and say, with that as a perspective, what would a facade that might last 100 years look like, and would it solve the problem? I mean, I think we sort of asked that question, but I think it's a rhetorical question in a sense. One of the issues of lifetime, there's a technical lifetime to components, to systems, to the building as a whole, depends on the quality of the construction, durability. There's an economic lifetime that may be entirely different. I think it was in Singapore, I was hearing stories of buildings that were 5 to 10 years old that were being torn down and rebuilt because the value of the land was so great. If you had a 10-story building on that plot of land and you could build a 20-story building, you tore down the old one and built a new one. So the economics often drive this. There's another whole issue here. I don't know what's going on in Europe, but in the US and some of the major cities, as a result of post-COVID changes, you've got an awful lot of buildings that are empty. And whether they're going to get filled up slowly over time, or they're going to get offices changed to apartments or torn down, or it's not clear, but there's a lot of discussion going on in that area. I'm going to, the last couple of slides, I'm going to start to talk more about the interface between the facade design and HVAC design, sizing, and cost. And the cost is going to start coming up as a key issue, because we're working in an industry where cost drives lots of decision making, for better or worse. And I'm going to talk a little bit about the envelope versus the structure. Well, actually, I just want to make the obvious, I think obvious point that there's wide variation here as well. There's a lot of interest, for example, in mass timber as a way of reducing the embodied energy and structure. At the moment, building structure is the dominant piece. If you look at the overall embodied energy, the envelope is maybe a decent second. I haven't quite figured out where HVAC systems come in. There's a lot of metal, there's a lot of materials in some of those. But those are all part of the discussion in terms of where one should put one's emphasis. The other issue here is lifetime. Glass has potentially almost, well, I shouldn't say infinite, but a very long lifetime, a single sheet of glass. IGUs much shorter. Curtain walls, which may be combinations of multiple things with motors and other things like that, are going to get even more complex. So this introduces the whole issue of the time cycle over which things are changed in a building. This is a graphic example of that from a company that looks at smart buildings. And I don't know, frankly, that these numbers are exactly right, but I think it's just a good indication. It's a good reminder that there's a lot of different cycles going on here. I pulled out the two that were sort of relevant. The facade number they give is 15 to 50. Seems logical. You could imagine numbers shorter than 15 and higher than 50. But in general, the HVAC is much slower, is much faster rather. HVAC systems are normally designed to be at least updated and retrofit and replaced, partly because everyone knows that a chiller is not going to last forever. So if you're doing a good job, you design it so you can pull it out later. The facades, I don't think people pay as much attention to that, and I'm going to come back to that in a second. So how do you prioritize investments over time in a world like this? I mean, if funding is available, then you can do everything. Of course, funding is typically, option 2 here is much more realistic. It's normally constrained. And so you want to optimize both short and long-term operation and goals here. And this sort of brings us back to looking at the building as an integrated system. That envelope doesn't stand by itself. It has direct implications to the HVAC system of the building, at least probably the structure as well. And then both of those are linked to the grid. And the key, I mean, there's a technical link here of all sorts, but there's an economic link, and that's the one that I want to emphasize. So we're always talking about, can we invest more in the facade to make it work better? But that's a smaller piece of a much bigger discussion about where investments go. So what I want to do is I want to optimize this yellow box on the left here. I want to put in better glazing. I want to put in smart glazing. I want to put in ventilating double envelopes. I mean, you pick your strategy of choice here. But it's going to cost more. And the normal routine is someone will say, well, what's the energy payback? What's the payback? It's 27 years. Nope, we're not going to do it. But the decision here has huge implications over here. And this is an expensive part of the building. And these days, it has equally important implications over here. So what I want to do is I want to make decisions on the facade that explicitly impact the HVAC systems and probably explicitly impact what you're doing here. These days, people are talking about putting battery storage in building. Well, if the envelope is optimized, maybe the batteries only need to be half as big as they might otherwise need to be. So I want to transfer cost from here to the facade and from here to the facade. And let me give you 2 examples where people are talking about that. This is from an architectural firm in Boston. They were looking at this, it's an airport, obviously, all glass facade here. And from a comfort point of view, not an energy sort of heating point of view, they put in this perimeter heating system here because this is a giant pieces of glass. And they didn't want people just to be uncomfortable near it. Well, if they went from double to triple glazing, they would have had roughly an equivalent comfort improvement, and it would have been cheaper to put in the triple glazing than it was to put in that HVAC system. But that's not a decision that's typically made. It's not an analysis that's often done, and not a decision that's made. So the value proposition for triple isn't just about energy and carbon. It's about a lot of other things. Also resilience. There's an interesting study in New York City. If the power goes out not for a few hours, but for a few days, people die. I mean, in Texas 3 years ago, 600 people died when the power went out for 3 or 4 or 5 days. Pipes froze, people froze. We don't design buildings to be resilient and get through that kind of thing. And there's a nice study there that shows in a New York City apartment how the temperature drops or how quickly it drops if you have no heat in the building. And you say, well, you can leave the building, but if it's a citywide event, you've got tens of thousands of people. So it makes sense to build resilience in here and pay a little bit more for that if you can. Another example, Empire State Building, fairly iconic building. 10 years ago, they started a project to replace the HVAC systems in this building. And someone said, wait a minute, what about the windows? Now, the windows happen to be double glazed. Now, this is a 90-year-old building. The original windows were single glazed. About 20, 30 years ago, they replaced them with double, but just double clear. So when they got around to doing the HVAC upgrade, they said, let's do something with the envelope. So they actually did renovation in the building where they took out 6,000 double-glazed windows, brought them down to a little factory they built on the 5th floor, replaced the double glazing with triple glazing, and then every morning they brought those windows back, installed them, and the next day people showed up in their office and they had triple glazing. Elegantly done. And then the payback was very fast. The reason the payback was fast was not just the energy savings, but because of this renovation on the thermal envelope, they were able to cut the HVAC costs. And they improved the solar optical properties. So they cut the chiller size and the heating size as well. So nice example of sort of looking at this from a systems point of view. So we want to push in this direction of getting better thermal envelopes. I'm going to just quickly go through a couple of examples here. This was grabbed from one of the Glass for Europe documents, looking at the offset, the increase in embodied energy going from, this was probably single to double. We're looking at that in the U.S. now for going from double to triple. The point is it pays off fairly well. We're trying to push in the U.S. 3% of the windows in the U.S. are triple glazing. And in Northern Europe anyway, it's code requirement. So we're looking aggressively at a lot of different options. I mean, VIG, obviously, if VIG was there, it's here, but it's not on the market in a practical way. One of the points, though, that we're looking at, instead of just a conventional triple on the lower left there, is this thin triple option, so that you're getting essentially the same equal or better thermal properties, but you're getting it with much less glass and therefore much less embodied energy. So these, again, in a colder climate, have embodied energy paybacks in a matter of months. A couple of companies now have started making these units. Nice properties. These are center of glass properties, but a triple. These are 2 Lowy coatings, argon or krypton filled. Quad unit, you can get numbers down like 0.4 with a quad, and the weight of these is just not much more than a conventional window. So these are things that are on the market now. Great thermal performance, lower embodied energy. And then the even more exciting in some ways is the renovation replacement market. If you've got a lot of money and time, replacing the facade is an obvious thing to do. But the obstacles for doing that are usually enormous. There's an opportunity to, I'll call it refurbishment here, interior add-on glazings, or possibly there's some people looking at exterior, but the interior is easier. This is that same thin glass. This is like 1 millimeter glass with a fiberglass frame, light enough that one person can hold it and move it around. And these things can be reinstalled on the inside of an office building overnight without, tearing out things, without moving people out of the spaces. So we think there's a huge opportunity. 40% of the buildings of the commercial buildings in the U.S. are single glazed, and essentially all of them are candidates for something like this. You can also tweak the solar optical properties of this as well, so you can address some cooling issues as well as the heating issues. And then the last point I want to get to in sort of looking at this interface between the glazing, the facade options, and the rest of the building is all those other neat things that one could talk about. This is a purposefully messy, complicated diagram in any given building. You're not going to have all of this stuff. But the thermal, I've talked some about the thermal stuff in red here. The point I want to make here, though, is we're now talking, and I sort of addressed some of this before, we're talking about a system between envelope and the rest of the building. You're not going to avoid lighting integration or HVAC with anything in the facade. You're going to have to deal with that. This gets complicated very quickly from an information point of view. So here's a sort of simpler variant. If you're looking at what's going on in the building in terms of design, you might have thousands of IGU options, dozens of curtain wall supply options, smart glass suppliers, shading systems. In the end, you've got numerous combinations, potentially, of systems that are going to have to be operating here. So I pick one of each and I install my system, and 5 or 10 years later, I need to fix it or change it or modify it. How do I know what's there, what's out there, what to do? The ability, the industry, this is an IT challenge. I mean, the industry's ability to track data and act on it later, I think, is generally poor. There's not a lot of good interface across all these players here. This is a change in the U.S. coming. I believe Selkowitz has something like that. This in Europe, this is Viricon. They encode a number on their thermal spacers, and 25 years later, if you go to that building and you say, let's fix this glazing, let's do something with this glazing, but you scratch your head and say, what was the coating, what was the spacer, what were all the other properties, you can, in theory, get it by punching that number into a computer and checking it out. So I think this data management issue, which we don't normally think about, is an important part. And I want to close with this as a bit of a theme. I did a little bit of work when I was a kid, almost, with Bucky Fuller, the guy who invented the dome. I like this sort of example that if you want to change the world, change a paradigm, you don't just focus on the problem, but you find something better, put it out there for people to understand and adopt and go with it. So I think we're in need of more sort of out-of-the-box thinking like that. There's been some interesting work in Delft. I'm sure there are people here that know a lot more about this than I do. Looking at the facade, and this is sort of encapsulating the themes I've been talking about, is thinking about the facade not just as a system, but as a service. So if the stuff is complicated, which it could be if you start putting PV and HVAC and all that in the facade, then have a company whose focus is delivering the hardware and then servicing it over time and operating it, and you do it, you pay for it as a service rather than you just buy the stuff originally and hope that it lasts for 20 or 30 years. So there's a thesis on this and lots of other interesting work. This is, of course, a theme that goes beyond facades, so I think it's something worth thinking about. So as a kind of follow-up, again, I promised you more questions than answers. I think we obviously want to innovate. If we think about the envelope as smart, simple, and active, the old expression, pick 2 out of the 3. I realize that simple and smart, obviously there's some conflict there. I think that it's critically important in a number of cases to look at smart active stuff, but you should keep it simple as much as possible. I talked about the performance operating versus embodied carbon. Those are obviously issues. Optimizing for comfort and appearance, that's what people still pay for. So it's a people issue as well as a building and a grid issue. And I didn't talk too much about this guarantee issue, but in that life cycle scenario, you need to be able to address performance over time. In New York City, there's now a new law which comes into effect in a year or two where they're going to, for buildings over a certain size, they will look at measured data. And if your building energy use per meter squared is above a certain level, you will pay a fine. And it doesn't say, well, was the facade bad? Was the heating cooling bad? It doesn't matter. It's just the total amount of energy. So we're moving in the direction of guaranteeing not just the U value of a window, but the energy use of the building. And all this stuff, I come from the technology world, but it's going to require innovation in finance and policy as well. And I think we'd like to learn as much as we can from smarter people in Europe and elsewhere. So conferences like GPD are great, and that's why it's worth coming here and talking to all of you. So these are a couple links to Mick and myself. Berkeley Lab, mentioned before, I'm retired, but I hang out there still. There's 40 years of papers and documents that are accessible online for free. Lots of tools, Window Therm Optics, Energy Plus, that hopefully most of you know about, Glass Database. And the Facade Tectonics Institute that Mick and I are both involved in on the board of directors, in an attempt in the US to try to bring some of these issues together for follow-up. So with that, I will close.
Super.